Good afternoon, everyone. Welcome to the two-day workshop for professional naval architects. On behalf of the Department of Ship Technology, I welcome you all to this panel discussion. Today, we have a panel discussion on developments and challenges in computational hydrodynamics, a panel chaired by Dr. Sadish Babu PK. Dr. Sadish Babu PK is an alumnus of the department, currently serving as the Associate Professor of the department. He completed his MTech from IIT Bombay and PhD from Department of Ship Technology. He has served the Indian Navy for over 22 years and retired as a commander. His areas of interest include ocean technology, material science, naval architecture, ship design, marine hydrodynamics, and corrosion engineering. We have an eminent panel of members for this discussion. Please join us on stage and take your seat on the dais. Dr. D.D. Ebenezer, retired scientist H and Director Systems of NPOL. A hearty welcome, sir. Mr. Vivek Ramnath, Chief Technology Officer, Smart Engineering and Design Solution. We are honored to have you with us, sir. Mr. Lijo T. Joseph, Senior Hydrodynamics Engineer, Aris Marine. A very warm welcome, sir. Mr. G. A. Surya Teja, Deputy Manager, Basic Design, Cochin Shipyard Limited. Very welcome, sir. Thank you, panelists. I'll now hand over this session to the panel chair, Dr. Sadish Babu Piki. Thank you.
Okay, thank you, Resmia. Good afternoon, everyone. I'm very happy that I got a chance to chair the session on developments and challenges in computational hydrodynamics. And I'm very happy that we have four very experienced persons who are working in CFD to be as fellow panelists. And it's a right mix of people from academia, scientists, and the management level, and actually who are doing the work from almost all major parts of industry based in Kochi. As you know, CFD as a technique is getting matured. And in fact, we can call it a numerical towing tank is being established in all the institutions. And Department of Ship Technology is also now doing very serious work in CFD. And when you come to marine hydrodynamics, the ships sails in water. So almost all the basic design involves studies in CFD, whether you take resistance prediction, powering predictions, maneuvering, seakeeping. You take anything, any basic design, naval architecture aspects, CFD has become now very, very important. Apart from that, we also have aerodynamics studies happening in ships to study the even the ventilation systems, the flow around a ship's deck, how the ship's exhaust goes out. So in that way, all the design houses are using the technology in the initial stage itself so that we are getting a very optimum design. But having said that, there are a lot of challenges. You need a lot of expertise. You need very costly softwares. And so I'm very happy that we have a very experienced panelists to share their thoughts in this regard. So I welcome all of you, all panelists, alumni members, research scholars, and students to these sessions. What we have planned is I will introduce one by one. They will give their thoughts for 10 to 12 minutes. After that, the floor will be open for any questions. Is it okay? Can we start with you, sir? So we'll start with Dr. Ebenezer, sir. He is a naval architect from IIT and is retired as scientist H, outstanding scientist from NPOL Kochi, and he is working in the department as adjunct faculty. And apart from his naval architecture graduation from IIT Madras, He has MS and PhD in ocean engineering from University of Rhode Island, USA. He has been spearheading a number of projects in the ship technology. He has been mentoring the PhD scholars, MTech scholars. We are also doing project with the Cochin Shipyard. Sir, I welcome you to this panel and request you to share your ideas. Okay. Over to you, sir.
Pleasure to be here. Today morning, when I asked some students to attend this, they asked me who's the target audience, and I replied the first target audience are the panelists, and the rest are those who will be sitting in the audience. Yeah, there's a lot to learn from each other, which is why there are conferences, and yeah, and industry, in my thinking, doesn't interact much with each other. They come outside and tell us only what's on the surface. If you dig deeper, there's a lot of things to know. Okay. So this is a workshop for professional naval architects, and I'm going to talk about what I think is the simplest problem that we have in this area. And the problem is um, optimization of ship resistance using computational aerodynamics. There are lots of things that are being done using computational aerodynamics, and the industry is doing that. So in my thinking, this is the simplest problem, and it is not just computation of resistance. It is the design of a surface ship hull with minimum resistance that meets other requirements. So the key word here is design, which we often use very liberally in the industry, saying that we have designed something. How would I define saying that I have designed something? So a design is the solution to a constraint optimization problem. We build houses, we design houses, then they may not in any way be the solution. They may not be optimum in any sense. But if you do try to find the optimum solution, then that's a very difficult task. And that is actually what we are going to talk about today. Okay. So what is involved in this particular design problem? I need to use computational fluid dynamics. Actually, you can think about experimental fluid dynamics in the same breath to optimize the underwater hull form and minimize the resistance. It's not just that, there are several constraints. Perhaps one very important constraint is the amount of time available for solving this problem. I mentioned CFD and EFD. If you say, for example, you give only 1 month and maybe $100,000 to both the CFD people and EFD people and ask them to come up with the best hull, the CFD people will do a much better job because there are many more options that we can try and we can choose the best among many variables, variants. Okay. Okay, there are many other constraints. For example, the hull should be fair and the displacement or underwater volume is more or less fixed with some small amount of tolerance. And I need to do other basic things which every naval architect does. But even without worrying too much about the constraints, the problem that is that we have to solve is a very difficult one. There are mathematical ways of stating this problem, but very often it is not done in a strict mathematical sense. Okay. So the way it is done is that we start with a parent hull and we create a finite number of variants. We don't have an infinite number of variants. We don't find any derivatives. We create a finite number of variants using mathematical tools and our sense of naval architecture about what is likely to be best, and you evaluate the variance. That for each of those variants, you find out what will be the resistance, and then you pick the variant with the minimum resistance. Okay. Even stated like this, which is a slightly watered down way, this is quite a hard problem to solve. So we have to choose the best among many competing candidate hulls. And what is the difficulty? It is not easy to find the resistance of even one candidate hull. A lot of effort is required to do that. And if you do it correctly, if you do it with much effort, it will take time. And the second part is that all the variants will have almost similar resistances. So the resistances of the candidate hulls differ only by a few percent. So in order to think about this problem in a somewhat simple way, you can think that you have a geometry scale with only centimeter markings. There are no millimeter markings. And you have some object which is, I say approximately say 6 centimeters long. And you're asked to find out which object is the shortest or best. You will find that you cannot use your geometry scale to find out which is shortest, because you do not have enough resolution, you do not have enough least count in order to determine which is the shortest. So the similar problem is there when we come to do minimization of resistance. But it's not just that. Every candidate hull that I need to look at has to be fair. And all naval architects are taught that your line should be fair. And whether or not your lines are fair, your professor will say, hey, this is not good and that is not good, and tell you to straighten some things out. But in a mathematical sense, it is not easy to describe what is fair. So this is written in a book regarding the geometry of ships, that fairness is very subjective, that you cannot mathematically decide what is fair. Okay. Now, but naval architects have built some tools, and here we can see what is known as the Korea container ship hull, and we are looking at it. We're looking at the C2 continuity, the second derivative on the surface of the hull, to see whether it's continuous. Oh, it's not bad. All my thick lines are somehow connected to each other. But if you want to create variants of a hull, you have to ensure that your lines are also continuous. That's not very straightforward. Okay. Now, when we are saying that we have a method to do this, to find the optimum hull, we need to develop what is known as a robust method. And this robust method should be, if it is really robust, a novice should be able to implement it. Somebody who is not an expert in finding the resistance of ships should be able to do it. Now, you all know that you may be very good at some particular task, but if you try to teach somebody else and train them to do it, then you find it difficult, because that person doesn't have much of a background in whatever you're doing. So if you can actually develop a robust method that a novice can implement, then you have done very well. For that, you may have to write down certain rules and illustrate it in many different cases. So it's interesting that all the software developers, they will give you tutorials, and you can see from the second point here that people who start using these software will find that the tutorials are not very useful for ships that are of interest to them. These tutorials run well for the tutorial, but they don't run well for the other case. That means whatever they are telling you to do is not a robust way of doing it. And that is what we need to develop. Okay. This idea is very important. Many of us in college think we calculate something, and that we find the answer to something. But in computational fluid dynamics, and even in all experiments that we do, we only estimate what the answers are. We cannot find out the truth. If I ask you to find the length of a pencil, you estimate what the length is. You cannot give me a number. You cannot tell me a answer to it. So whenever I estimate the resistance of many candidate hulls, there are error bars associated with each of them, and I'm trying to compare which one is best, and therefore that's a difficult task. All college students will be familiar with this. That this is a Gaussian distribution where I make several measurements of the same object, and I come up with several different answers. And if I plot all of them, they will lie on some Gaussian distribution curve. Similarly, if you find the resistance of a ship using computational fluid dynamics, using many different meshes, you will come up with different answers. And each answer, if you plot, you will get something which looks like a Gaussian distribution. From that, you can find out a mean value. There are some other techniques where we want the mesh density to go to infinity, or the mesh size to go to zero, some other techniques. But finally, you will end up with an estimate. And nowadays, every measurement that you do or every calculation that you do has to come with an error bar. If you do not give me an error bar, I do not consider the number that you are giving to me as a result. Therefore, obtaining these error bars are also very difficult in computational fluid dynamics. So we learn how to estimate and learn how to keep the error bar small. Okay. So one of the problems is that we have to create variance. I have a parent hull, it already has something good, maybe in operation, but I want to create variants to see whether I can make one that is better. And there are some approaches, some standard methods which are described in naval architecture books. One of them is known as a Lackenby method. And you will find that the implementation of the Lackenby method is different in different software. Therefore, you will attempt to do the same thing using different software and come up with slightly different hulls. Usually what is done here is that we say that, for example, I want to move the longitudinal center of buoyancy forward or backward in an effort to change the shape of the ship. If I move the LCB forward, the hull will become fuller in the forward region. So I say, I want the LCB to move forward by 1%, and different software will give me, starting from the same parent hull, they give me different hulls. All of them will have the same LCB moved 1% forward. Therefore, I don't have one handle, I don't have one parameter to describe my variant, which becomes difficult when you want to compare many variants. So to deal with some of these problems, one thing which is used very much in the industry or in fact by all computational people is known as the Richardson extrapolation. In this figure, you can see what results are obtained here. Mesh 3 with a coarse mesh. Mesh 2 is finer and mesh 1 is finest. So you keep making your mesh finer and finer. You hopefully get answers which lie on a curve, and then you can extrapolate your answer and find out what will happen when the mesh size is zero. This method is so important, there's even a book written just on Richardson extrapolation. Okay, but there are challenges if you try to use it, because it is not easy to hold certain things constant while you're changing certain things. I'll not go into the details of it. This Richardson extrapolation is a lot harder to actually implement in a very nice way than what first appears at first sight. This is a very interesting figure. It shows a compilation of results done by people across the world. And that line which is running down the middle, the dashed line at zero, that's an average value of several experimental results. And many computational people are trying to find what the answer is using their numerical model. And on the x-axis, you got number of grid points. It's in million. So here, somebody is using 4 million, 8 million, 12 million, and somebody is using 36 million, close to that. And they all give you the results. And you can see that some of them lie very close to that red dashed line, but some are far away. We did our own work in our department, and all the circles that you see here are from our work. And we know we have developed techniques to get closer and closer to the truth. So we know how the mesh should be developed in order to get results which are very accurate. And you can see that one of our results is the black dot. One of the results is the black dot, and it is very close to the error, to the average value, maybe less than 0.5% error. Okay. One of the things that we have to do in computational fluid dynamics, the first point that I mentioned is time. the time available to solve a problem is to choose a turbulence model. If you see today in industry, most of the people prefer to use what is known as a K epsilon model, because it requires a less number of cells, and therefore it will run faster on whatever computing facilities you have available. But the K epsilon model has got inherently its limitations, because it does not model the sub-viscous layer very well. There's a layer, very fine layer in any turbulent flow, which is close to the ship hull. And that part of it is modeled in the sense that we assume what is happening there. And that assumption we know is wrong, especially when we are using the K epsilon model near the aft of the ship. But time prevents me from using a better model. So this is kind of a low-end computational fluid dynamics model, but that's very popular in industry, because that's all the time that we have for running it. Okay, so some limitations of the model are mentioned in books, but I will not go into that. Okay, so when we are trying to solve this problem, we need to develop good methods, and we need to develop methods that are robust, which a novice can use, but at the same time these methods should ensure rapid convergence to the correct resistance. Otherwise your iteration will keep running and running, maybe for days or nearly a week, but you will not get convergence to the correct answer. The thing is that we have a problem to solve, which is maybe 100 million by 100 million matrix you are solving by iteration. And here is the result for one particular case. And you can see that with a lot of effort, we developed a very good mesh, and therefore the convergence is very good. People seldom show you how the results converged, even in the journals, because it's not good. And whatever is not good, they hide, and they tell you what they want you to see. But we've developed some robust methods, and so we are able to do this very well. Okay, so to conclude, it is quite difficult to solve even the simplest problem in computational fluid dynamics. Okay, that is optimization of ship resistance. You want to find the resistance of given a hull, to find the resistance. So I'm not considering that as a problem, because optimization is the problem. To find the resistance of one ship, yeah, we can do that. Okay, but to find the best one, that's lots more difficult. Numerical results will usually give a result. So many people buy expensive software, or they use open source software, garbage in, garbage out. They will get an answer, and they will tell you that that's what I got. And usually there is no way of checking whether what they have done is right. Nobody knows the truth. You don't have experimental results. You don't have C results, whatever. Okay. So because of that, in industry and generally in the computational fluid dynamics world, tall claims abound. People say that I've done this and that, but even that includes journal papers, but they are largely unsubstantiated, which means there's no proof for what they say. They claim a lot of things, but there's no proof. So yeah, those are just my ideas, and thank you very much for your patience.
Thank you very much, sir. I think like a professor, he has explained a typical resistance problem, and he has covered the challenges, the different methods, and the problem you might face if you don't mesh properly. So I think there will be many questions. We'll have the question interaction section at the end. So thank you, sir. So now, next speaker is Mr. Vivek Ramnath. He is one of our distinguished alumni member. He is employing many of our students here, both BTech and MTech. Presently, he is working as a Chief Technology Officer at Smart Engineering Design Solutions, SEDS. And it is based in Cochin only. He is, as I said, he is a BTech in Naval Architecture and Shipbuilding from this department. And he did his MS in Offshore Engineering from Newcastle University, England. His fields of interest include mechanics, fluid dynamics, acoustics, and electromagnetics. Vivek, I'm sure SETS has done a lot of work in CFD. And I would also like to congratulate SETS for completing the first anti-submarine warfare project indigenously built for the Indian Navy. And luckily, I was also part of it in the beginning. So you can I'll welcome you to give your remarks.
Good afternoon, everyone. I hope I'm audible. First, let me tell you something very frankly. You just listened to an expert. I will have to disappoint you there. I'm just a user of, all these tools. I'm basically a ship designer, and hydrodynamics is one element, or one step towards that goal of a efficient, optimized vessel. So, Dr. Satish Babu introduced where I come from. And it is always a pleasure to be back. This is my second home. And I am very happy to see the young faces, and among there are many familiar faces also. I see Sachin, who was our employee, and he was one of the persons. So I'll show you a few examples of the work which we have done, and he was one of the major contributors. So probably I will direct some of the questions if it comes to me to him. Yeah. So that thank you for coming. Yeah. Okay. So before I start the presentation, what I thought was how the industry sees this problem of hydrodynamics and of large fluid dynamics. As you know, any problem we have, for the simpler problems, we can look at analytical solutions. We have an equation, for example, a cylinder in a stream. You can calculate. We have algebraic. You have analytical solutions to some of the simpler problems, like a cylinder in a stream. You can calculate the float flow force and probably the radiation diffraction effects. But the moment the complexity increases, you'll have to look at alternate options. And what used to be done was to look at scaled model test experimental methods, or in some cases prototyping, which was very difficult for the scales we talk about, like for the ships. For some other industry, for example, aerodynamics, aerospace, prototyping is a method even used today. So, the advent of advanced computing capacity, starting from mainframe computing in 60s and 70s, when aerospace started implementing it in their work routines, it joined the marine and offshore industry much later. We are one of the most conservative and the last to adopt these kind of technologies, any technology, if we look at it. And I think largely the industry started using fluid dynamics in a computational way in the late 2000s or early 2010s. That's what I have seen. And as Dr. Ebenezer said, one important thing that many times industry misses is a validation. Rather than, we just do some calculation, a numerical prediction, get some color plots, garbage in, garbage out. There's no validation against actual experimentation. There's no value to it. So one thing, when we started in the industry to work on computational fluid dynamics, was to mandate validation against actual experimental results. Be it a ventilation problem inside a trunk, we ask the users to give us results. We put some sensors and give us some results. We benchmark it before moving forward. Fortunately for SETS, we have a parent company which is 80-year-old with some 600, 700 ships built. And we have a lot of data in terms of model test results and sea trials of various parameters. And in that way, for marine hydrodynamics, we have a wealth of data. We only need to find time to validate some of those. And I'm quite sure Sachin was part of our team who was, doing from very slow steaming, what do you call, bulk carriers to high speed semi-planing vessels, fast patrol crafts. We have done some good validation with very good benchmarking, very good, matching of results. So I'll go into the slide. So I come from sets. You might know to some extent what we do. Pictured is one of the bulk carriers which was built to sets design in China. I'll just give a very brief, keep it very simple and brief. We'll have a very brief introduction of where we started off and what all simulations we generally carry out, and specifically on fluid dynamics. Okay, I wouldn't go into the details of all of these. I just wanted to say that our footprint is now more or less 50% in the commercial marine bulk carriers. We have a research vessel project going on now. We have a lot of, we had passenger ships, large passenger vessels. Actually, many of them were built by our friends in Cochin Shipyard. Now we have a lot of projects in all the major shipyards in India: Hindustan Shipyard, Garden Reach, Mazagon Docks. We are also working with other shipyards, major shipyards in India. Of course, we have multiple projects in Cochin Shipyard as we talk. So that's where we are. We are now really full of projects, and I believe will bring a lot of opportunities for you as you graduate and move on to industry. So I just wanted to say which are the areas that we work on in terms of simulations. Fluid dynamics is obviously one, solid mechanics, acoustics, and electromagnetics. What connects all these is the method, the numerical approach that I earlier mentioned. Most of the fluid dynamics problems you can handle with RANs, most of them. Solid mechanics with stiffness equations. Acoustics mainly uses Helmholtz equations, and electromagnetics Maxwell's equations. So what you're trying to do is to reach an integral or a differential form, so that you can computationally solve it, and then go into the. But each of these domains have its own challenges. This platform today is for fluid dynamics, so I will not go into the details of it. But each of them has its own set of different challenges. Okay, we'll go into the fluid mechanics part. Why I put this picture is to show that bulbous bow, and you can think about the the runs, the optimization runs it had to go through to reach this level. You can see it's a fairly large one. It's a kind of a medium high speed, I would say, for this size of a vessel. It is 80 knots plus vessel. It's a 157 meters long, 1,200 passenger vessel. This was the photo taken during just before the launching of the vessel in Cochin Shipyard. Okay, now coming to the hydrodynamics. When we look at the problems that the industry wants to resolve by various things that what a ship design industry or a shipbuilding industry wants to know about ships. Obviously, the resistance, how you can optimize the hull form to achieve minimum resistance, the propulsion, how selection of a propeller, how can you have the best efficient propeller behind the hull to get the most the best powering performance. How to, for example, many of the vessels that we do, research vessels, have very stringent seakeeping targets. Your vessel motions, because one is for the crew, because the crew is engaged in very critical laboratory measurements, and it should be comfortable for them. Second is for the instruments. They're very sensitive to vessel motions, and also for example, slamming. So there are a lot of conditions that have come attached to these projects when it comes to seakeeping. Another big problem is the maneuvering of the vessel, because there are cases where again when I will just very briefly touch upon it, but maneuvering is one problem even today So we work with almost all the major model tank basins in the world: Marin, HSVA, Crisol, David Taylor. And maneuvering is one problem we have still found even the best in the industry are struggling to replicate, not just in the numerically, but also experimentally. We had a very recent case where a model tested, uh, maneuvering prediction. When we went into the full trials, far off, very, very far off. Fortunately, on the good side for us. We were worried that we will go far off, and we were pleasantly surprised that nothing happened. So we had to go back to the same people, but they were clueless. So I must admit that in this, especially in the maneuvering where there's complex interaction of fluid with the vessel control surfaces, you still have a problem. Before this, I just want to show that matching of the experimental and CFD results that we did for the 500 passenger vessel. I've not kept the values for the resistance, but Sachin can vouch for me that these are accurate figures. We got very close to now. And another thing is, as Dr. Ebenezer said, predicting the resistance is not a challenge anymore. We are getting very close to the actuals. 1% difference, which is not a challenge, because see what we have done is we have validated a huge range of vessels of multiple sizes. So we have a very good correlation. And so getting a value per se is not a big challenge. Whereas optimization, yes, it remains a challenge. And I'll come to that. This is a validation that we did for the Potsdam propeller, the open water characteristics. I'll just show this. I put some videos so that, people sleeping here can, wake up and probably take a glimpse. Okay, now we talked about these three methods of analytical, numerical, and experimental. Of late, last 4 or 5 years, we are also seeing a new approach where you can, instead of a complex solution where a brute computing force is employed to solve the Navier-Stokes equations, you can have a reduced order model by parameterizing the inputs and then matching the output. So you basically run multiple cases, hundreds of cases of this, making small tweaks, and then allow the a reduced order model or a surrogate model to be made. And basically what happens is you are trying to find a match between the various parameters used as inputs and outputs, and then use machine learning algorithm to have a regression analysis of that thing. And then finally, it should be able to predict, and it learns through this process. So this is an approach which is getting traction in every field, not just in hydrodynamics or in general CFD or fluid mechanics, but you go to any area. This is the trend that you see as we have more and more computing capacity, where you can run hundreds and thousands of these simulations. So this is a bulbous bow optimization, which was done with the parameters that you see. It was not fully done within our premises. So we had a long discussion with the people who, on this, and we also, verified and validated some of their claims. So as Dr. Ebenezer said, that 13% is a claim by the tool provider. But of course, we see 4 to 5 or even slightly up to 8% is what we have seen best in the bulk carrier, which I showed you earlier. We had a wake equalizing duct wherein we found a reduction of 8% in power by adding that. Okay, sorry. Aerodynamics is something which we have done comparatively less because the requirements are less for a ship designer. But when you look at, for example, a defense project where you have multiple antennae sensors on the deck, and you have very high powered engines, putting plume out into the decks. Two things. One is so what you're seeing there is a concentration of the carbon monoxide on top, and how it is coming to the deck. Another thing is basically you can also look at the temperature profile. For example, the thermal impingement, secondary impingement on the deck or on the surfaces, how much is coming uh, which can result in infrared signature of the vessel. So this is the bottom one is basically a qualitative analysis between actually a frigate's um, funnel, the plume, which was verified by a CFD prediction. Okay, so these were some of the problems which we studied during various problems, various actual problems which are raised. So the bottom left one was basically a problem when the exhaust gas was scrubbed, or basically they mix the exhaust gas with seawater, they sprinkle it, and they the effluent, or basically the wash water, has H2SO4 in it because it is H2O plus SO2. So that sulfuric acid, when it comes to the sea, there's this requirement that it is balanced by the alkaline sea within about 4 meters. So that was tested using a titration model, and that's what is shown there. And the back pressure from engines, back pressure to the engines from various exhaust mechanisms can be studied. Again, we validate these with actual, various by matching various parameters, temperatures, pressure, velocity, etc. Turbo machinery things. The ventilation studies on the right is for a defense project we did. We had quite good results as long as you validate and correlate it. The above one was a Flettner rotor, which was tested at IISc wind tunnel. So we were involved during the concept design phase of that, and we got some very interesting and results about, with that. So this general purpose works. And this one is quite an interesting thing. It is not a validated one, but what we tried basically is a simulation of a smoke and fire, basically heat transport and using a large LD simulation. The purpose was we were involved in the uh, design, or basically of a high pressure water mist system in one of the tunnels which is getting constructed in India, the Mumbai-Pune new expressway, which is coming below the Lonavala Lake, about 10 kilometers long tunnel. So the challenge was to simulate a tanker fire, 200 megajoules of heat coming in the tunnel, and whether the high pressure water mist system can attack it and control it. So this during that exercise we tried on various options like this. So this is just a simulation that we tried out and tried to validate. Okay, I think some works I just wanted to show you what we are doing in the industry. Pleasure to meet you, and we can have some of those questions. I can direct some of them to him. Okay. Okay, thank you.
Okay, thank you, Vivek. Very interesting to see that a lot of CFD work is being done at SEDS, and I'm heading a technical team at SEDS. I'm sure it was a very challenging job for Vivek. I think as I said, we'll have discussions towards the end, whatever questions. Now I would like to move to Mr. Lijo T. Joseph. He was a hydrodynamic engineer with over 10 years of experience in CFD. He's actually a mechanical engineer, but he's done his master's in ocean engineering from IIT Madras with Professor Ananda Subramaniam. And we were colleagues for some time. Now he is working as in the hydrodynamic engineer at Ares Marine. I know that he's fully involved in CFD. He's leading a few people, experts in CFD. I think he's must be one person who is doing only CFD, isn't it? Like, naval architects, we do many things. Like I know Surya, like you're doing stability today and tomorrow. But I welcome you to the podium and share your ideas.
So good afternoon, everyone. Am I audible? Okay. I have only few slides, so don't worry. We'll finish it soon. Okay. So I'm working with Aries Marine. So I'm working in the field of, as sir mentioned, I'm working in the field of computational aerodynamics. So I just want to present some of the works we have done so far. I just want to share some information with you. So oh. So these are some of the, we know this computational hydrodynamics has become an crucial role in the field of fluid mechanics. So because we can see that the applications of computational hydrodynamics here, if you look at the slide, in the ship hydrodynamics itself, a lot of applications are there, like resistance, propulsion. And if you move to offshore and coastal engineering and renewable energy, a lot of applications are there. I'm not going to deep into it. I'm moving to another slide. So basically, these are the works we are doing in the field of computational hydrodynamics. So the first one is power prediction. The power prediction of the vessel. The power prediction of the vessel includes the ship resistance prediction and self-propulsion parameters prediction, like wake fraction and thrust reduction. And the last one is the open water characteristics estimation for open water efficiency. And all these factors leads to the power prediction of the ships. So that is the first one we are doing as a part of CFD. The second one is EEXA study. So it's basically energy efficiency existing ship index. So IMO has put forward some regulations regarding the emission of green gases. So the IMO has put forward some regulations to bring down the emission of these green gases. So actually we are trying, like the existing ship has this existing ship has this compliance with this IMO regulations. So that's what EEXA study means for. Coming to the second point, that's scrubber wash water study. Like mentioned in the earlier slides, the scrubber means exhaust gas cleaning system. So IMO has some regulations like the wash water coming out from the scrubber has to get diluted as per the IMO regulations, IMO regulations range. So we are checking in that, checking the same with that scrubber wash water study. And the third thing is air lubrication. As you can see from the figure, the third one, that is quite interesting because in the air lubrication system, what we are doing is we are releasing the air from the bottom of the hull. So this air forms a thin layer between the hull and the water. So that results in reductions in the frictional drag that leads to power reduction. Actually, it accounts for 5 to 10% of overall power reduction by using this air lubrication system. Since it's reducing the frictional drag, this system is applicable for those vessels which is having the lower foot number, because at lower foot number, this frictional drag will be prominent when compared to wave resistance. So this system can be applicable to the vessels which is having lower foot number. So that is the air lubrication system. So when we comes to this motion analysis part, that is fourth one. There we are checking the ship's 6 degrees of freedom in response to environmental loads. Environmental loads like waves, winds, and currents. So how this ships reacts and how in all directions. I mean 6 degrees of freedoms. So we are analyzing that in the for the motion analysis part, and those things we are comparing with the IMO regulations. That motion, I mean, the results what we are getting is in compliance with the IMO regulations. So the fifth one is mooring analysis. As you can see, the vessel is tied in various direction. So in the mooring analysis, what we are doing is we are actually finding we are estimating the type, I mean, the type of mooring lines and also the number of mooring lines required and the capacity of mooring lines so that the vessel can hold its position when it in response to the environmental loads. So when the environmental loads hits to the vessels, it will have some movements. So this mooring line is actually meant to restrict all these movements. So we'll be designing this the mooring lines based on that. And the final one is something related to aerodynamics. That is a helideck analysis. So again, as per Civil Aviation Authority, they brought out some regulations regarding the turbulence variations in the helideck. So actually, we are checking those things whether this helideck, I mean, the new design of helideck is in compliance with those regulations. So these are the projects that we are doing in our firm. So these are the softwares we can use it for the computational aerodynamics. The first one is the Rhinoceros is a modeling software. There we can model I mean, it's a CAD modeling software, but by using some plugins and all that, we can find out the hydrostatic part of that. The remaining all things are completely hydrodynamic softwares like SASCM, Moses, Orcaflex, Optimor, OpenForm, ANSYS, COMSOL, and Cadence, etc. Okay. So when we comes about talking about the challenges in computational hydrodynamics, the first point is computational time. The computational time means if our problem is bigger, I mean, if our problem is complex, we need, I'm not very clear that you may be knowing about the cells and all that. FEM methods, you're aware of it? Okay. So if the problem is too complex means we need to analyze the more area of interest. If the area of interest is more means our domain of analysis will be more. In that case, what will happen is our computational resources requirement will be more. So those are one of the challenges. If the problem is too complex means our computational resource requirements will be much more. So um, uh, so if the computational resources is much more means that will increase our computational cost. Otherwise, if you have the existing computational resource means the analysis requires the I mean the if you have the existing system means the analysis time requirements will be much more. That are the main two challenges we are facing because talking about the high performance computing system for bigger industries, it is feasible to have this high performance computing system. And if you talk about the smaller industries, or if you are talking about the research firm, this accommodating this high performance computing system is much more difficult. So that is one part of challenges in terms of computational time and computational cost. The second thing is regulatory acceptance. The regulatory acceptance means what all things we are doing in CFD. I mean, in terms of computational aerodynamics, that should be that should be submitted to this class. I mean, classification societies. We need to. I mean, the regulatory means this classification societies. We need to get acceptance from the classification societies for all the works we are performing. So that is one of the challenges. The next thing is expertise dependency. Since if we are using so many models, I mean, so many turbulence models and so many solvers we are using in CFD. So picking up the right one, the right models, the right solvers, and in between any errors happens to finding out the exact solutions, there should be always a expertise dependency will be there. So that is one part of challenge. So again, if you are for accommodating an expert is again leads to this cost part that will increase the cost part. So actually, all those things are interrelated. And the final one is validations and verification. So the waterworks we are doing in CFD, that should be properly validated. So not to get the exact data, like it's not possible. I mean, it's always not easy to get the experiment data or exact experiment data for the work we are doing. It's not possible. So sometimes that will become this validation part will become a challenge for us. I mean, challenge for everyone. So coming to the development parts, again, same thing, high performance computing. If we can accommodate this high performance computing means this we can reduce the computational time, and we can go deeper into the much more complex problems. So next one is AI assisted mesh generations and parametric optimization. Again, if this AI assisted mesh generations and parametric optimization will be there, means that will again reduce the time constraints, and our optimization work will be much more easier. The third one is the greater compliance with, again, greater compliance with classification society. So nowadays the computational hydrodynamics has become much more advanced. So we can accommodate this high performance computing system, so that we can go for high performance models, turbulence models, high performance method. So as a result, we can have greater compliance of results with the classification societies. The fifth one is, as I said earlier, better predictions of complex phenomena. Like if we have this our resources, we have a good high performance resources, we can go ahead for the complex complex problems, and we can get the better results. So actually, all these challenges and developments are always interrelated. So that's it from my part. So thank you. Thank you.
Thank you, Lijo, for summarizing the work you have done. I know you have purposefully omitted technical part, I can see, because maybe because of the but you have brought out the challenges and the opportunities in that thing. Thank you. Okay, next speaker is Mr. G.A. Surya Teja. He is very familiar to the audience here. He very routinely briefs our project with Cochin Shipyard with Dr. Manoj, Dr. Abhinay sir, and all research scholars are doing. So I just, for the benefit of audience, I would like to introduce Mr. Surya. He is currently working as deputy manager in Cochin Shipyard Limited in the basic design department. He holds a BTech degree in naval architecture and marine engineering from Andhra University, College of Engineering, Visakhapatnam. He also have an MTech degree in ocean engineering and naval architecture from IIT Kharagpur. He has over 4 years of experience in ship design, and I think you have done a lot of work in Cochin Shipyard in the area of CFD. So we look forward to hear from you.
First of all, thanks for the opportunity. Yeah. So basically, I want to put as a basic design. I'm coming from basic design section from shipyard. So I want to just put our perspective and our journey in CFD throughout these years, and how we are doing in CFD, and what are the challenges, and what are the emerging trends in CFD. So before going to that, I would like to highlight, like my professor already used to say, naval architecture is naval architects. Basically, they call jack of all trades but master of none. So basically, you have this, you do this cantling calculations, you do this powering, you stability, everything. So, but when it comes to advanced studies like FEA, CFD, generally in India, traditionally it's used to be an outsourced. But I think FEA in such they are already ahead, and we are also slowly trying to pick our this thing in FEA. But somehow CFD took a backstage. That also we want to, come into picture. That's what we want to move ahead in the CFD area also. So it all the journey of the CFD started with your alumni only. His name is called Vishnu Ara. So he is 2016 relieved. So he happened to go to IT Kharagpur for attending a seminar on open foam. He did some 3-day seminar and he came back and introduced CFD to CSL, then basic design. Then it picked up from there. Then I just want to present how we moved from there so far. What are the challenges and all. So like our previous panelists covered, if you see the simulations in the shipbuilding, then we would like to categorize like standard, complex, and unique simulations. So standard means you can go to the next slide. Basically, traditional ship design, you need to have this at least this set of simulations to go ahead with the design. Basically, it involves model testing, or you do a CFD, resistance speed power curve. Ultimately, you get the speed power curve. Suppose if it happens to be a shallow water vessel, you need to do a shallow water resistance simulation. This is a traditional for every project. This is required to be done for getting confidence in your model testing. If there is no model testing, that is the other case. If there is model testing, you can validate. But if there is no model testing, it's better to have these things, because nowadays we are seeing vessels where regression methods also is the vessel dimensions are in such a way that the regression methods also is falling. Like you cannot apply those regression methods for this new type of vessels which you are doing. So these are some complex simulations which are like roll decay, sloshing simulations, propeller cavitation, slamming loads. This requires high computation capacity, highly nonlinear problems. This often it's required for very sophisticated vessels only. We often don't do that as a citizen. This is a complex part which, let's say, propeller cavitation and all will be mostly designed from the OEM side. But if you want to do from your own perspective, there are you can validate. There are so many test cases available, but these are mostly not done in house. Actually, and these, like our previous panelists have presented, there are free fall lifeboat simulation, there is exhaust plume simulation. Nowadays, these alternate fuels also is coming into picture. So you have this dispersion studies. That is, this recently we did a fuel cell catamaran vessel where the dispersion of hydrogen needs to be studied. So these are some of the use cases. I think some I might have missed, like energy saving devices and this new air lubrication simulations also. But mostly these are the typical applications of CFD in shipbuilding. So coming to the challenges, as highlighted, it is CFD is highly intensive. It needs high computational resources, and there is a skill required. Unlike other disciplines like stability and all, you need to know what you are inputting in CFD and understand the results. You need to verify, and there is a validation and uncertainty. Actually, for CSL, we have a model tested data and CTRL data. In that aspect, we have wealth of data. Then, of course, the software license costs. Each of the commercial software costs a lot of money, and maintaining is also lot of charges, lot of cost it is. So these are the main challenges. So in our case, how we are using CFDs, basically whatever concept designs we are doing, we are using CFD based power prediction along with if there is an regression methods applicable, we do that, and on top of that we conduct CFD also. Then in basic design phase also, we are using CFD together with hull form parameterization. We recently acquired software called Chassis. We were trying to optimize the hulls and the test in CFD. Then for some projects, we also have used conducted simulation to get wake fraction and thrust reduction, which I'll be showing. The special analysis part, we have not yet moved there, but soon, like we are planning in future to increase our hardware capacity and slowly venture into that special analysis part also. Now we are only doing this concept and basic design part. So some of the projects which we have done, I just want to highlight. Based on the shallow water vessel we were doing. So it's a there is no model test basically, but we have a task of designing the propeller. So without more, so this hull form is tricky. It is having the stern tunnels to accommodate large propeller dia. So we don't have any model test data. So we need to get the wake fraction and thrust reduction. So no regression method is available for giving W and T wake fraction thrust reduction for propeller design. So we use CFD to get those wake and thrust reduction. And one of the second example is in one of naval vessel we found out that maneuvering course keeping stability is not so that good. So we need to have this ventral fin design to improve the course keeping. Then we studied the resistance effect on its resistance, and we aligned the ventral fin. Then one of the naval vessel we optimized, we created a fully parametric definition, and we did a CFD based powering study. And these are some other simulations which we have done. One is this AUV long simulation. This was required for one project where you have to see when it is being launched in a containerized form on the transform of the vessel, like a free fall like boat basically. So we wanted to study how the path taken by AUV, but now that concept has changed to David Long's. It was only a preliminary study. Then we also use other studies include like some of the concept designs we worked out. We were using TFT to see, you can see the bottom picture, there is a tunnel given to accommodate large propeller dia. So we are using CFT to check whether with what speed the tunnel is getting entrained with water. If it is not the case, then we have problem in progression. So this is how we are using CFD in our use cases. Then parallelly, we are also working to enhance our capability. Like sir said, Satish sir said, we don't have a dedicated CFD per se, but we wanted to, when we are doing CFD, like previous panelists conveyed, you need to do verification and validation. So you have there is a lot of data available, which is like RISO, KCSSL, DTMB, across the range of rule numbers. You have an open source, open domain models where you have a resistant data available. We try to verify and validate. Then we also happen to participate in the blind workshop. I think there is this institute called JORIS, Joint Research Institute. It is formed by a group of companies, including some renowned testing tanks and some other various ship design outfits. Where what they're trying to do is they're trying to they found out some vessels, namely tanker, cruise vessel, and some tugs. And during dry dock, they tried to 3D scan the hull, applied paint, measure the roughness, and they did a proper feature. The idea is to validate the efficiency of the CFD code at least up to the self-propulsion simulation. So we happen to participate in one of that case, which is a resistance workshop only. Then we are engaging with like QSAT. We have a project coming with QSAT on open form, research on open form. Then we are also having this BTech and MTech projects where we are also giving some of the use cases which we have found, let's say we got some problem with the steering wheel in one of our vessels. So the rudder torque is so much. We calculated based on IRS rule, but it came out very large during the rudder was getting locked at certain angle and it's not coming back. You need to lower the speed to get the rudder back. So we wanted to check what is the rudder torque. So we were like that, like those problems when we are facing, we are trying to collaborate with academia and trying to understand the scope and length of the problem. So these are the efforts we are doing in CSL. So so far we have been using this open source tool, OpenForm only. So I would also highlight the problems we are facing with OpenForm. The advantages are obvious. free, full transparency. You can extend the code for research. It is very good. Scalability. You can because everything is available. You can include your own libraries, your own set of code if you are a good programmer. But the downside is since you mostly are coming from user side, you mostly apply the thing. The one problem is meshing. Like you need to have this proper boundary layer meshing. We often fail the traditional measure that comes with OpenFOAM. And for ship resistance simulation, there is this current number dependency. So the solvers still depend that the formulation is semi-implicit so that you cannot take much big time steps basically. Basically, if you see the ship resistance or ship self-propulsion problem is a steady state problem. We want to march the solution towards the final steady state. So that way in OpenFOAM we feel we are lacking. So we are not able to march the solution like other commercial softwares. I think this is emerging. This is the new things that we are seeing in CFP. I think this ML and AI topic already covered in the previous one. What they are trying to do is you create a parametric variation, number of variants, and you do this design of experiment. Basically, you do, let's say you have a 2x2 simulation parameters. First, you do design of experiment. Means you are not minimizing any function, you are evaluating everything. Basically, all combination of parameters, you are running simulations and just storing data. Using that, you go to next level, which is optimization phase, so that you don't stuck in local minimum, local, minimum or local maximum. By doing this, you will be able to evaluate more variants in the design space, then enhance turbulence modeling. Recently, people are looking at using AI to easily to accelerate the CFD conversion. Basically, ultimately, the CFD or whatever these numerical methods are approximations, numerical approximations. Ultimately, we are trying, we are, converting, discretizing this equation, converting the partial differential to algebraic form, then finally assembly these equations and solving in an iterative way. So there also there is this AI going on to increase the acceleration of the iteration phase. And this digital twin and this generative design optimization also is kicking. Basically, you will try and you need to have data for that basically. You will try in lot of parametric variants, and for a given parameters, it will directly give you a hull form. But that still it is in early phase. We were doing some consultancy from London as we London, they are doing this generative design for merchant vessels. So, okay, when this is what we see as a way forward. Basically, I think CFD now it's no longer an optional thing in design houses because now to give an optimum design, it's not that you find the speed power, but it also requires you need to give an optimum design to owners. We need to be if we need to be competitive with design houses abroad. I think we need to have that all skills. Like we need to be able to give optimized designs for which you need skills in alpha optimization, skills in CFD, confidence in CFD results. I think these are the ways which you can, kill the people and make get that environment. One is through like industry academia collaboration is very much needed. I think as CSL we have a lot of use cases which we try to give to MTech students, like the rudder problem I told. So every time we have this practical use cases which we can use our own talent. Then I think there is a new ministry, this Indian Technology Center that is being proposed. I think with that, we also feel that will solve some of our R&D problems with respect to, that high specialized studies. So with that, I would like to conclude. Thank you.
Thank you, Surya. Very interesting. And I really like the last slide, way forward. So, dear students, there is a shortage of experts in CFD and hydrodynamic experts. So, So we also thank CSL for funding that Center of Excellence. You purposely did not mention or no? No. You didn't mention. Okay. 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 So I think the all panelists have given their initial presentations. So we have some time left. So now the floor is open for any for the interaction with the panelists. Please pass the mic.
Any questions?
Yeah, thank you all the panelists for your wonderful slides and all. My question is to Ebenezer sir. So you mentioned in a slide, we can use K omega, K epsilon model and SST K omega model. So I was just wondering, what is the comparison between this K epsilon and SST K omega model, like result wise and computation time? Any idea on that?
I would say approximately 3 times more in terms of number of cells. Yeah. And yes, in in terms of the size of the matrix, it goes up. But we know that K epsilon doesn't work well near the aft of the ship. And I also always want to remind that we can use back of the envelope calculations and find out our CF values and estimate the resistance in 5 minutes. So why do I want to trouble myself with a CFD model which I know is not great?
Yes. Just a perspective, probably, Professor Abhinasa can correct me. Like when we did, this hydrodynamics and aerodynamics problems, I think it's more about the boundary layer, the difficulty in creating the, correct boundary layer with K epsilon. That's what you were saying, right? So probably with, where the boundary layer challenges are less, probably K epsilon. So we have done many cases with K epsilon, especially aerodynamic problems, Yeah. So hydrodynamic problems when the boundary layer simulations are very important. Actually, we know that. I think it's always the first choice is to go for SST.
Omega SST.
I think this K omega model works well for the regions away from the boundary layer, whereas this, K epsilon works better for the region away from the boundary layer, whereas K omega is better for the near boundary layer. But this K, what you are telling about K omega SST, right? SST K omega, it's a combination, I think, because it works well for the near and far region and interpret the this buffer zone. Yeah, generally the buffer zones are not good, but this if you are incorporating this K SST K omega means it works well for the near wall and away from the wall, and also interpret the data in the buffer zone. Right, sir? Okay. Okay. Okay, that part is answered, I think, right? Okay.
Time, we can talk in terms of number of times rather than absolute time. So K epsilon, if it runs in, let's say, half a day, the other thing may take, let's say, 3 days, 6 factor of 6. No, the thing is, as I put in one of the slides, we only know that if the method is good, I can trust the result. If my method is not good, how do I know whether the result is good? Usually, I don't have any other comparison at that point of time. I don't have an experimental result.
Okay. Any questions, Shruti?
So my question is to Vivek sir. In one of your slides, you had shown in this ML and then a bulbous bow on the right, and then you had a pie chart on like percentage. So what you are trying to say that you had implemented that in creating that bulbous bow, or you had that regression analysis and everything back up your data in creating that model?
So basically that pie chart shows what percentage, those are all the parameters that were explored in the design of experiments, and what was the influence of each parameter in from the original model to the optimized model. So the idea of that pie chart is basically, so it was done using Fine Marine. Now it's a cadence tool, it was Numeka. So basically the tool itself, one of the feature of the tool is also to give what percentage of each parameter. So basically you can, when you do this, you can find out what is the, say for example, you can avoid some of those parameters which are less important, less influential, and you can concentrate on those parameters which are, prominent. So that's the idea. So that pie chart shows you, gives you an idea what factored or what resulted in that improvement results.
Okay. Any more questions? Lijo, you were mentioning about that air lubrication. Is it being actually done at Aries? Can you explain something about that project? It's a ship, small, it's a ocean vessel.
It's a tanker actually, sir. I don't go into detail. Lubrication, air lubrication. So air lubrication generally means, as I said earlier in the slide, it's like releasing the air, pumping air out from the bottom of the hull. So what is happening is it creates a thin layers of air bubbles between the hull and water. So what happens, there won't be a direct interaction of water, waters and hull surface. So that way we can reduce the frictional drag of between the hull surface and the water. So, as I said earlier, this frictional drag is prominent when the speed is very low. Speed low in the sense at lower speed. The speed is getting higher. The frictional this wave drag become prominent, and the frictional drag will come down. So this method is actually being used for the vessel. Having less fruit number. So in that case, if it is proceeding in lower phone number, means the frictional drag will be prominent. Otherwise, this method is not applicable, because if speed is higher, means this air bubbles and these air bubbles coming out from the hull won't stay there. So there will not be a formation of some this thin layers and all that. So it's applicable for those vessels. It's an air lubrication system, because air is acting as a lubricant between the hull surface and the water. Yeah, it's a big system actually. Yeah, additional power is required. Like it's releasing air in the bottom is some additional requirements is there. I'm not going to the technical part, because we are much more interested in the flow region part. So
Manoj sir, any? Okay. What percentage of reduction in resistance do you see by introducing the 10%? Okay, so my next question is to Mr. Vivek. What are the challenges with that maneuvering? You meant like maneuvering, you face challenges with simulating it using the CFD, right? What are the challenges? Can you elaborate a bit on that?
Okay, so some of the challenges are even for large model test basins. So we generally, for all, now we work on a lot of projects where the clients are European. So they also mandate that they have to do the testing in marine or HSVA. So very internationally reputed test basins. They have their own methods in addition. So they do a CFD simulation. They also have some other panel-based methods and various methods to do, because it can save a lot of time. They have large core machines, etc. The specific challenge in the CFD domain was, the separation. For example, when especially during the what do you call zigzag maneuvers, for example, when they predicted the second, the overshooting of the this thing, what they predicted, and finally what we achieved during the sea trial. So we had a model testing for this as well in their facility, as well as a CFD prediction plus their own methods. So what I was trying to say is the comparison of, rather than going into the detail, because it was done by them, not by us. So we found a large difference, and this we see very regularly. So sea keeping is still okay, but maneuvering we still find a big challenge, even for the best in the industry, to have a fairly accurate prediction. So yeah. I think LES was employed, especially during separation phase. So we had some discussions on this, because we were also not very happy with finally what came out, because we had to do a lot of extra work to ensure, we assuming that this is going out, but finally nothing happened. So we went so there was LES. So there were the preliminary predictions without the separations were with RANS solvers. Then there were some separation studies when LES was employed. Even with their high, so they have some 6,800 core machines, HPCs clusters, and they can use it across multiple locations in the Europe with tie-ups. So they did some even DES simulations for more accurate these things, but we were not really seeing much of a So what I'm trying to say is always be very careful when, even with the model scale, variation from the actuals, we have to be very careful with how we find out, how we read from the results. That is what I was trying to bring up. I can try to, if you are interested in discussing, I can further figure out, and I can look into the details of it, and maybe we have a separate discussion on this. Correct. Yes. Are they comparing to a model test or an actual sea trial? So that was the difference here. See, we got a fair comparison with the model tests, but the sea trial was far out.
As he said, luckily on the positive side, not on the other side.
Once the project is over, nobody talks about it. Because building science is.
So I have one question to Surya. You mentioned about a national initiative on Ship Technology Center. But Ship Technologies? Indian Ship Technology Center. Can you briefly elaborate? The students may not know about it.
So it's basically, before it was called NSDRC, right? Like National Ship Design Research Center. So as a part of this maritime fund, which has been announced recently, some around 79,000 crore. So this shipbuilding R&D is one of the agenda. So I think around 300 crores was allocated for doing R&D. So they started a new, basically renamed this NSDRC as ISTC. So this is to skill people and, solve this typical research problems. So many design houses may not be able to afford this high CFD costs and the computational resources. So the idea is to have this ISTC doing R&D for this hull form optimizations and other R&D studies. so that it will help in India in giving good designs and good R&D capabilities. You can add yes.
Yeah. So why this was set up, ISTC, the Ship Technology Center, was now the government is now focusing on shipbuilding. There's a lot of onus from the government of India, and they have set up specific panels under the blessings of the DG Shipping has now set up multiple panels on studying the problems in ship design, shipbuilding, and trying to fill the policy gaps. They can only fill the policy gaps. The implementation has to happen at the industry level. So one of the policy gap, or one of the gap which was found was skilling people. Now itself, I think we are finding a huge challenge in finding people. So I think for the next several years, I think the people coming out into the industry, they'll have a lot of work, at least for the next 5 to 10 years. I think there's no dearth of work. So one is skilling, not just design, also in shipyards, for example, semi-skilled and everything. So this ISTC focuses on multiple areas. One is skill of manpower. So there will be different courses. So I think it is getting they are organizing it. IMU plays an organizer part. When Professor Shiva Kolundu is the in charge of it. And the old campus of NSDRC is also presently, I think they will eventually move out. We don't know, but presently getting in place. Mr. Anthony Prince, who is our CEO, is a member of the panel set up by the government in setting this up. So I also get to know things because many of the work he assigns to me. So that's why I thought I will add my 2 cents in this.
CEO is main member of anything. Okay, any more questions? Students, research scholars. Can we, sir, it's okay. Can we conclude any? It's okay. So it has been a wonderful session. All we had Dr. Ebenezer, Mr. Vivek Ramnath, Mr. Lijo, Mr. Surya. So on behalf of the organizers, thank you all very much for sparing your valuable time. I know how much difficult it is to spare half a day from industry. So thank you very much. Thank you, Lijo. Thank you, sir. So I also thank all the audience for not sleeping and making the interactive session very lively. Thank you. Thank you once again. I'll hand over to Resmia for concluding this.
Thank you, panelists, for such an engaging section. Now we'll give away a certificate of appreciation to all the panelists. I would request Dr. Sadish Babu PK to present the certificates. First, I would request Dr. D.D. Ebenezer to receive the certificate. Now I would kindly request Mr. Vivek Ramnath to receive the certificate of appreciation from Sadish Babu sir. I'd like to request Mr. Lijo T. Joseph to receive the certificate. I will request Mr. G. A. Suryateja to receive the certificate from Sadish sir. Now I request Ebenezer sir to present the certificate to the panel chair, Sadish sir. That's the end of today's panel discussion. We have light refreshments provided outside. Please feel free to enjoy. Thank you. Have a great day.